Hi. Uh, in this lecture, we're going to begin our discussion of Unit 3, focused on solving systems of linear equations. In this unit, we're going to um, explore a number of the key ideas associated with solving linear systems of equations. At the end of the unit, we will understand both the so-called row picture and column picture of a linear system and its solutions. We'll be able to translate between a system of equation form and an augmented matrix form of a system. We'll be able to use Gaussian elimination to solve arbitrary systems of linear equations, whether it has a unique solution, whether it has many solutions. We will be able to identify when there's no solution or many solutions or a unique solution. And we'll be able to express the set of solutions in the case when there's many solutions in a parametric form. We will also begin to explore solving real-world problems with linear models using the tools of Gaussian elimination. In this first video, I want to spend a little bit of time developing an intuition for what linear systems are, what their solutions mean, and so on, primarily from a geometrical perspective. As a reminder, what is a linear model? When we talk about a linear model or a linear system, a linear model is a mathematical model that is described by a linear system of equations. A little bit of a circular sort of definition there. But there's two key points. The point is that it's a model described by a system of equations and that that system is linear. Remember that a system of equations is a set of equations that use the same variables, and not just the same symbols for variables, but variables that mean exactly the same thing. This is one of the key things about a system of equations. The variables have the same meaning in the context of whatever problem we're working in, and they must take on the same value in each equation in the system. Right? So if we see an x in one equation and x in another equation, they have to take on the same value in that system, right? Okay. So that's what it means to be a system of equations. A linear system is, to recap what we've seen before, simply a system in which every equation is linear. All of the terms are of the form some constant times a variable, a times x, or just a constant by itself. We've introduced the idea of what linear equations look like in an earlier video. And to recall, the general form of a linear equation in 2 dimensions is that of a line. We can rearrange the sort of the standard form for a linear equation in 2D into a form that matches a form of y equals mx plus b for a line with slope m and intercept b. A system of equations is then a set of lines. Solutions to the system are values of the variable that sort of satisfy both equations at the same time. These are points where the lines intersect. When we have 2 lines, the most common situation in 2D is that these lines intersect at a single point. An example here, 2 lines rearranged into a form of y equals mx plus b, and these 2 lines, one with a slope of 2/3 and a y-intercept of 2, and the other one with a the other with a slope, so one of a slope of 1/4 and a y-intercept of 2, and the other with a slope of 2/3 and a y-intercept of -1. These meet at a single point highlighted here, which happens to be the point 7.2, 3.8. every point along this red line is a solution. It's a pair of xy points that is consistent with this second equation. Every point along this blue line is a pair of xy points that is consistent with the first equation. As a system, a solution has to satisfy both equations at the same time. That is the points that are on both lines at the same time, which is the single intersection point. And you can imagine that if you take an arbitrary two lines in two dimensions, they will usually cross at exactly one point. They will usually have a unique solution. There are special cases, however, where lines either don't intersect or where they intersect at more than one point. Parallel lines, that is, lines that have the same slope but a different intercept. Right? These two equations lead to sort of a y equals mx plus b form with the same slope but different intercepts, both a slope of 2/3, but the blue with an intercept of -1 and the red an intercept of 2. These two lines will never meet. They're perfectly parallel. If they never meet, they never intersect. There can be no point that is on both of these lines at the same time. Right? Since no point is on both of these lines, this system has no solution. All right. It is less likely for very unlikely for two random lines to be parallel, but in many systems where there is more sort of structure, parallel lines can absolutely arise. Now, a very special case of parallel lines is overlapping lines, lines that have the same slope and the same intercept. These are lines that are, when we're written in standard sort of linear equation form of some ax plus bx equals c, have equations that are related by a multiple. They don't have to be identical, but they have to be perfectly related by a multiple. So 2x minus 3y equals 3. 4x minus 6y equals 6. The second equation is simply double the first. In this instance, if we try to plot these two lines, they are the same line, right? If they are the same line, then every point on this line is on both of these lines, satisfies both of these equations. This is a system that has many solutions. In fact, an infinite number of solutions, because a line is infinitely long, contains infinitely many points. That doesn't mean that every point is a solution. We have to be on this line, but there are an infinite number of them. There are multiple ways that we can try to express a set of solutions where there are infinite numbers of solutions. One way is to use what we call parametric form. We use some parameter, usually a different symbol than the variables in the problem, to represent the freedom in the set of solutions. So here I will use that as t. And then we come up with an expression for each of our variables in terms of that parameter. One of the easiest ways to do that is to recast the problem, the set of solutions, as the line we're interested in, y equals 2/3 x minus 1. And then simply say, let's let x equals t, and y would then be 2t over 3 minus 1, giving us this set of solutions. We'll discuss this parametric form in more detail when we get into actually solving systems and methods for solving them. Those are the cases for two lines. Two lines in 2D either meet at one point, or they're parallel and never meet, or they're overlapping and meet at every point on the line. When we have three lines in 2D, so three equations in a two-dimensional space, it is rare for them all to intersect at the same point. I have a sort of visual here of where I've added one more line to the pair we had before. So again, we have the same two that we had in the earlier example, but I've added a line shown here in cyan with a slope of -2 and an intercept of -1. These lines intersect, but never at the same place for all of them. Two of the lines intersect here. Two of the lines intersect here. Two of the lines intersect here. There is no point where all three lines intersect at the same place. That means there is no point that simultaneously can satisfy all three equations. There is no such point. The system has no solution. This is very commonly observed in 2D. The most common result for three lines in 2D is that there is no solution. The lines don't intersect at a common point. However, in special circumstances, they can. To generate this system, what I've done is I've taken the system we had here, and I just kind of moved up this blue line, changing its intercept but maintaining its slope. Kind of imagine just taking this blue line and shifting it in this direction. And when we do that, we can shift it until we have exactly one intersection point. I've constructed a system here where we intersect at exactly one point. Now, doing that gave me kind of a weird number for the intercept because I had to get things absolutely perfect to have them lie on top of each other, but it works. Once we have this system, we now have three different lines that actually happen to intersect at a single point. This system, again, has a single intersection. The system has one unique solution. Happens to be at -4/3 and 5/3. All right, so those are a number of examples in 2D with sets of lines. 2 lines, 3 lines, with intersections, without, and so on, to give you a flavor of what linear systems in 2D look like, what the solutions might look like, what they can be. Let's move a little bit into 3D, where things are harder to visualize, but there's a tremendous amount that can be learned from them. Limiting yourself to only 2D problems and visualization really limits how much intuition you can have for linear systems. 2D is very special, and moving into higher dimensions opens up a lot of new possibilities in the kinds of solutions we can have. So the general form of a linear equation in 3D, given here, is the equation for a plane. And we can actually think of the coefficients in front of the variables as being a normal vector, a vector that's perpendicular to the plane. And B is related to the idea of a y-intercept, although not in exactly the same form. So if one linear equation in 3D is a plane, then a system of linear equations is a set of planes, and the solutions to that system, points that are on both planes or all of the planes at the same time. And again, these are intersections. The two planes that I have shown here correspond to the two three-dimensional linear equations written here. And these intersect along a line, the line here. Every point on this line is on both of the planes at the same time. That means it's a solution to both equations at the same time. It's a solution to the system. It's a line. There's infinite number of points on a line. There's infinitely many solutions to this system. Again, we can write this in a parametric form. Because our answer is a line is a one-dimensional object, we end up with one parameter to describe that. Right? Let's not worry at this particular point of how we get this solution. We'll be exploring this further on down the line. This parametric form is a very common way to describe lines in 3 dimensions. Unlike a line in 2 dimensions where a single equation can describe that, y equals mx plus b. In 3 dimensions, the parametric form is one of the most common ways to describe a line. Okay, so not only does this system of 2 planes in 3D intersect in a line, most cases when you have 2 planes in 3 dimensions, they usually intersect in a line. Right? Just imagine of taking 2, say, sheets of paper and rotating one a little bit with respect to the other. They should sort of intersect, and if you were to imagine how their intersection in 3D, it would be along a line. Now, once again, there are some special cases. Parallel planes, that is, planes that have the same normal vector, represented by the same coefficients or simple scalar multiples of the same coefficients for all of the variables, but different offsets from one another, that is, different right-hand side constants, are perfectly parallel. They never intersect. It is impossible to find a set of coordinates that is on both of them. You can make sense from the equation form. Anything that satisfies the first equation would have this x minus y over 2 minus z equals 2. By definition, then, x minus y over 2 minus z cannot equal negative 15. This sort of system has no solution. Parallel planes do not have a solution. I will mention here sort of briefly before going to the 3-plane case, there also is the special case of having 2 planes that actually overlap with one another, essentially being the same plane, where you get infinite number of solutions everywhere on the plane. I didn't try to draw one because drawing 2 overlapping planes is a very, very hard thing to actually kind of visualize. Now, what about when we move to 3 planes in 3 dimensions? I've shown 3 planes here. I've added one more plane in the sort of the yellower tinge here to the 2 planes that I already had. The line of intersection of those first 2 planes is along here. The line of intersection of this pair of planes is shown along here. The line of intersection of these pair of planes is along here. And these sets of 3 intersecting planes, which each pair has a line of intersection, these lines actually do come together at a common point. These 3 planes intersect at a single point. There's one point that is at all 3 planes simultaneously. This is the solution, the one unique solution to the system. Given here, we will develop the tools to find these solutions. This is what usually happens in 3 dimensions. If you take 3 randomly oriented planes in 3 dimensions, the most common outcome is that they intersect at exactly one point, just like this example here. Okay. Now, there are some other cases. You could imagine 3 planes has where one of them is parallel to another, obviously has no solution, and so on. I am not going to try to draw the picture of a fourth plane in 3 dimensions. You can already see that this is starting to get very busy. A fourth plane makes it quite difficult to visualize. But if you just try to imagine, if you now take to this system and try to add a fourth plane here, what is the likelihood that that fourth plane would actually also pass through this point? It's very rare. Most cases where you have more than 3 planes in 3D, they usually don't intersect. There might be intersection points for 3 planes, but not for more than 3. Again, there are special circumstances. You can construct a fourth plane that happens to go through exactly this point, and that system would, of course, have a solution. All right. So that's a couple of examples in 3D to start to give you a feeling for what it means to be a system of equations in 3D and the sorts of solutions we have. From these examples, we can generalize an intuition. Systems of linear equations represent sets or groups of so-called flat geometric objects, lines in 2 dimensions, planes in 3 dimensions, and the extensions of these to hyperplanes in more than 3 dimensions, which are hard to visualize but share this flat property. The solutions to systems of equations are points where all of the lines or the planes or the hyperplanes in the system intersect, or all of them. That's the key point. Now, here is one of the very essential points, lessons that we can sort of glean from those examples. Linear systems may have a single intersection point and therefore a unique solution. This is something that often happens. We may have lines or planes or so on that are parallel. And if there's parallel planes or parallel lines, there can be no solution. For cases where we have larger number of lines or a larger number of planes than the geometry, right? I'm at 3 lines in 2D, 4 planes in 3D, and so on. It may be that there's no common intersection point, that there's intersection points for pairs or triples, but not for all of the objects, and thus no solution. Right? So we can have a unique solution. We can have no solution because of some of the things being parallel. We can have no solution because they simply don't share a common intersection point. Nothing's parallel. They just don't all come together at exactly the same point. We also can have cases where these objects intersect along a line, along a plane, or so on. And in that case, we have an infinite number of solutions, and that we can represent that in parametric form. There's no other option. A linear system cannot have a finite number of solutions other than 0, no solution, or 1, unique solution. Right? There's no way you can make 2 lines intersect at exactly 2 points or exactly 3 points. In order to achieve that, they would have to be curved. They would no longer be flat. They would no longer be linear. Right? So we can, this allows us to really focus our attention on a small number of types of solution. Unique solution, no solution, or an infinite number of solutions represented in a parametric form. And we'll discuss all of these in more detail once we get into the methods to find these kinds of solutions. Now, there's another way that we can also look at linear equations. And this alternative view involves linear combinations. Let's take a system of equations in 2 dimensions here. And here I've taken just the left-hand side of a system. We've seen how we can write such a system as a matrix multiplied by a pair of variables, where each equation has coefficients corresponding to each row of this matrix. But we could also write this system in a way where we decompose it by the columns of this matrix. I can take the first column and make that a vector, column vector 2, 1. And I take the second vector and then make that a column vector 3, negative 1. The scalar multiple x of this first vector would give 2x, 1x. And the scalar multiple y of this second vector would give 3 and negative y. And we add these together, we would get exactly this left-hand side of the system of equations. Right? So we can represent this left-hand side of a system as a linear combination of vectors, and those vectors are just the columns of the coefficient matrix that we have seen before. Adding in a right-hand side to this left-hand side, we take a system of equations like this, and how would we write this? Well, this system could be written as x times the vector 2, 1 plus y times the vector 3, negative 1 equals the vector 5, negative 5. What is a solution to the system then? A solution is a pair of x and y that satisfy these equations. That means it's a pair of x, y that satisfy this linear combination. Solutions to the system are the scaling factors that we need to express this right-hand side as a linear combination of the columns of this coefficient matrix. We can think about a linear system as an attempt to take linear combinations of vectors to find a right-hand side vector. And those vectors are, in fact, the columns of the coefficient matrix. Let's think a little bit about what this kind of means geometrically. So let's take exactly this same example and see what we really mean by this. Decomposing this system, writing it into this sort of linear combination form, we are asking for a multiple of 2, 1 and a multiple of 3, negative 1 that when we add them together will give us 5, negative 5. So let's sort of see what this kind of means geometrically. I'm going to plot our first column, C1, 2, 1. Our second column, 3, negative 1, C2. Scalar multiples of C1 have to lie along the line. Right? They just change the length, and if they're negative, also reverse the direction, but they have to lie on a line that this vector falls on. Scalar multiples of C2 have to fall along this line. Where's the right-hand side? The right-hand side is 5, negative 5 here. What does it mean to add together a linear combination of 2, 1, or a scalar multiple of 2, 1 and a scalar multiple of 3, negative 1 to get this? It means we need to be able to write a parallelogram that has one side that is parallel, that is along C2, another side that is along C1, and that when we connect from the origin to the corner of that parallelogram, we get the answer. Right? And this is represented here. If we multiply C2 by 3, we extend this line to here, to 9, negative 3. If we multiply C1 by negative 2, that moves us over here. Negative 2C1 is negative 4 minus 2. If we add together this vector and this vector, negative 4 plus 9 is 5. Negative 2 plus negative 3 is negative 5, exactly where we need to be. and we have this visual representation. The solutions to the system are the scaling factors that we need so that we can express this right-hand side as a linear combination. Right? They tell us how do we have to stretch this vector so that we can construct, and this vector, so that we can construct a parallelogram where this point is satisfied. One more example. What does it mean when we don't have a solution? We saw that one of the examples that can have the possible outcomes is that we don't have a solution. Let's take an example that doesn't. Here is a system of 3 equations in 2 unknowns. Right? In the original view, we would look at this, we'd say, oh, this is 3 lines in 2 dimensions. Each of these is a line in 2 dimensions. 3 lines in 2 dimensions often don't intersect at a same point. When we recast this as a linear combination, though, what the space we're living in is in a 3-dimensional space. Right? The columns of the coefficient matrix have 3 entries, 3, 3, 2, 4, 2, 1. The right-hand side has 3 entries, 1, 1, 4. Let's plot all of those. Well, column 1, 3, 3, 2, in 3-dimensional space sits here. In column 2, 4, 2, 1, sits here. The right-hand side, 1, 1, 4, is here. This is a system that doesn't have a solution. There is no way that we can express this. We can see this actually by noting that these first 2 equations both have a 3x. They both have a right-hand side of 1, but they have different coefficients in y. The only way that both of these things can be true is if y was 0. If y is 0, then to make this true, x has to be, should be 1/3. 3 times 1/3 is equal to 1. But if we then plug in 0 and 1/3 into this last equation, we get 2x plus y is 2/3 plus 1/3 plus 0 is 2/3. It isn't 4. We don't have a consistent solution. Why is this geometrically? Well, what does it mean to take linear combinations of C1 and C2? We can shrink C1, we can make it longer, we can extend it along the other direction, but we can't make it move off of this line. Scalar multiples of C1 have to stay on this line. Scalar multiples of C2 have to stay on this line. If we start now combining those scalar multiples to make parallelograms, to have a possible sum, all of those combinations have to lie on the same plane. Let me just try to show a couple of examples here, if I can. Right? So imagine that what we imagine that where we started was here. Right? Imagine that we took a scalar multiple along that line and another scalar multiple along that line. Where would the result end up? Well, we would have to sort of draw a parallelogram out of these 2 lines, and the solution would be at that corner. On the plane, on kind of a line connecting these 2. And if we go through and we ask, what about some other ones? What if I extended this line a little bit further? Well, then the parallelogram we would end up with would extend a little bit further, but it would still be on this same point. All of the possible linear combinations of those 2 vectors, C1 and C2, lie on a plane that I have represented here kind of by these dashed lines in between them. They can actually extend in the other directions of these sort of lines. They don't have to be in between the 2 vectors if we start taking negative multiples, for example. But They have to be in that kind of flat expanse. This particular right-hand side is not on that plane. Right? If we try to draw a line from this point, how do we, it's actually, that if we can think about drawing a perpendicular line down onto that plane, it is not, it doesn't sit on the plane. In a case where the right-hand side does not lie in the same plane as the two column vectors, we don't get a solution. That's what it means to have that. Right? Think about this. What is this? This is a combination of two three-dimensional vectors to give a third. It's going to be, if we think about taking two vectors and take a arbitrary or a random right-hand side, what is the chance that this right-hand side actually lies on this plane? Pretty small. The usual case for trying to find a combination of a vector in 3D as a linear combination to two others is small. It usually will have no solution, just as a system of three lines in 2 dimensions usually doesn't have a solution. All right. So that was just a little bit of a sort of introduction to 2 different ways geometrically to think about a linear system. One of them, the first one, is often referred to as the row picture. We say that because the key way we look at the coefficient matrix is along the rows, reading out the coefficients as an equation in a linear equation in the appropriate dimension. This row picture gives us an idea of systems of linear equations being sets of flat geometric objects, and solutions to those systems as being points where all the lines, planes, and so on intersect. Another way of thinking about it is often referred to as the column picture. Here we focus on the columns of the coefficient matrix, and we think of a linear system as an attempt to represent a given right-hand side as a linear combination of those column vectors. The solutions to a linear system in that case, then, are the coefficients of such a linear combination. I've written down here what it means when we do have solutions. We can also think about what it means when we don't have solutions. The lack of a solution in the row picture means there is no single point. There is no point where all of the lines or planes all intersect simultaneously. In the column picture, the absence of a solution means you cannot write the right-hand side. You cannot express the right-hand side as a linear combination of the vectors, of the column vectors of the coefficient matrix. The right-hand side does not lie in the same plane or sort of equivalent in higher dimensions of those columns. All right. This discussion was a very qualitative one, focusing on starting to build an intuitive geometric understanding of what systems of linear equations are and what their solutions look like. In the next components of this unit, we will develop the tools to actually find such system solutions. Thank you and goodbye.